Okay, can everybody hear me? Hello. If somebody can just confirm that if everybody can hear me, that would be great. Oh, fantastic. Thank you very much, Martin. So hello and welcome to the next session in the Neo4j Tech Talks, following on from the previous one by Liu on getting started in Docker desktop, Neo4j desktop. And this session is going to be on reactive database connections with Neo4j drivers. And my name is Greg Woods, and I'm a software engineer on the drivers team at Neo4j. And today, I want to share with you one of the really exciting features in 4.0, which is the reactive connections. So let's dive straight in by first looking at how query execution works in previous version of Neo4j. So we typically have our client, right, and our server, client being one of our Neo4j official drivers. And obviously the server being Neo4j, right? And what typically we want to do is query that lovely data we've got on the server by running a cipher statement against the database. So we run our statement, and then immediately afterwards, we're interested in those results, right? So we send a message to the server in the background in the drivers to request that all the records for that query be returned to the client. And then the server obliges. We get back record after record from the server until either all the results have been returned from that query, or until there's some sort of connection problem and the server can't get through to the client. And I want you to think about this for a moment, an analogy of a river. So think about the water as the data. Think about somewhere up in the mountains being the source of our data Neo4j server, and then somewhere downstream being the client. And think about it, a river has a fixed capacity relative to time, right? So there's only so much water that can flow down through this river. And if the rainfall in the mountains hasn't been so great recently, and it's well within the capacity of the river, then there's no problem, right? The water flows downstream and into the ocean without any problems. But if there's been a particularly rainy season or a rainy period, and the rainwater is above the capacity of the river, then we ended up in this flooded situation, which isn't any fun at all. Bringing this back to the data world, obviously this flooded situation is happening on the client, and that's because the client can't handle or isn't able to keep up with the pace at which the server is sending results back to the client. So what can we do about this? Well, we could try to speed up our client, so we could optimize our code. We could potentially, so we could optimize the code, finding every little inefficiency and trying to eliminate it. We could instead provision greater resources on the client, so we could maximize the amount of memory we've given that application or the CPU, max out the CPU. But this might not help at all, because we might be depending on a third-party system, where a third-party API that might be delaying us, and we're not in control of that, so we can't do anything about it. But even if we did increase the limit of the resources we have for our clients, this isn't really efficient anyway. So since we have to provision enough resources to cope with all this, the biggest amount of data that the server could be throwing back to us. So this is how it works in 3.5. This is a little bit of an exaggeration of the worst case situation. We have a little bit of protection in the TCP layer, but obviously this layer isn't aware of the abstractions of records and Neo4j types and so forth. Right, so that brings us on to how query execution works now in 4.0. Again, we have our cipher statement, which we want to execute against our server to achieve our results. And this time we can specify the amount of records that we want to receive. So here we're asking the server to give us 2 records from that query. And then obviously the server obliges and sends back a couple of records. And now the client can take its own time processing those records. And when it's ready, it can request some more records. And this time we can continue doing continue this again until either we've we've got all the results from the queries that we exhausted all the results from the query, or until some connection problem again maybe, or until we can actually gracefully terminate. We can send discard the remaining items on this query. And then bring this back to that river analogy, or the water analogy. This is like having a big dam across the results from our query, right? And in this dam, we have this gate which allows us to control the flow that comes out of this out of this query. So if our downstream parts of the river are looking like they're going to get flooded, or they're at reaching capacity, then we can close the gate, or slow the flow at least, to give the downstream elements a chance to catch up with the flow. And then likewise, if the client can handle all that flow of data, then we can open this gate as wide as we want and let the client handle it. But the crucial thing here is that the downstream, the amount of flow is controlled by the downstream elements of this system. And just to bring this again back to the data world, I wanted to show you what kind of impact this has on memory performance. So what I did was I wrote a simple application in one of our Java drivers, and we are able to, in 4.0 version, switch off this nice pulling in batches of records from the server, and then switch it back on to see how the performance handles it. So I wrote a simple application which does a big query and has some simulated delay in it to simulate maybe a third-party API taking a long time every now and then. And then I profiled the memory for that application. So here we're seeing the heap memory for that application. We ran just under 30 seconds, and it used about 300 to say up to 800 megabytes of memory. Now, what happens if we switch on the reactive, the automatic pulling of those records? And what you're seeing now is the effects of those records piling up at the door, because I've simulated delay in our application. And then you see these big drops when the garbage collector gets around to clearing them out. So if we switch on the reactive element to this, we see a vastly different picture where the memory usage is much more optimized. So we've gone from a peak of nearly 800 megabytes for a peak maybe of 60 at the most, and a very much gentle line. So yeah, so this kind of shows you what kind of things could be possible with using the reactive drivers, and essentially that's because it's pulling those records as it needs them, rather than just pushing them all when it's ready. Now, the core principle that makes this all possible is reactive and reactive programming. And whilst we can't build a comprehensive understanding of what this reactive thing is in 30 minutes in this session, it's enough time to give an intuition for how this thing works and to understand the benefits, right? So we've already seen that one of the benefits is memory management. Another one is increased simplicity in your concurrency models. And we'll look at these briefly, but I encourage you. I've got some links at the end of this slide deck, which will give you nice hook points into how you can dig out these things a bit more for yourself. As normal with these kind of abstract ideas, it's much better to get your hands on them and play around them for yourself. So essentially, reactive programming is programming with asynchronous streams of data. Right, so we're all probably familiar with, as engineers, familiar with the streams of data. And now this thing really becomes your first-class citizen in your coding. And this follows a change in kind of style of programming from this imperative style, where you have steps in your code, you have some state, and you have steps in your code to manipulate that code step by step. Whereas now we're following a more declarative style, where we're defining the behavior we want in our code, and changing those from that definition of the behavior. We're driving our application's behavior. So let's look at this example I've got here. So this line represents a stream of data, an asynchronous stream of data, and then data items can appear on that stream of data. So this circle can represent an integer or a Boolean, a string, or even a Neo4j record, right, from a query. And then we can have many of these things appearing on this stream. So now we have a kind of original stream. How do we do processing on it? So one way is we write code which reacts to changes in this stream. And let's use this example of a filter function. So we're going to want to have a result stream that represents our completed computation. And this filtering function, we're looking now for to filter out anything that isn't a circle, a green or blue circle, right? And yeah, so we got a blue one, we copy it over. We get a green one, we copy that one over, and then so on and so forth, ignoring all the other ones. So that's kind of a very simple, gives you a simple flavor of how this reactive programming stuff works, right? And just to note, this documentation style is quite popular in reactive code. This is some documentation taken from the Reactor core docs, which is an implementation of the Reactive Streams API, which I'm going to touch on in a second. And yeah, I just want to say this is a common way, an intuitive way to understand how these processing happens on these streams. So this is another kind of filtering function. This time we're filtering on distinct elements, right? So we're copying a yellow, green, a yellow, blue. Oh, we've already seen green before, so we can ignore that one. And one other thing to mention here that is this in this notation is this black line, which symbolizes the end of a stream. So a stream can be infinite in length, in time, but we can also mark a stream as being finite, and then after that point in time, no more elements will appear on that in that stream. So we can chain these functions together to build our desired application, change these reactive functions together to build our complex logic. And to get a more concrete understanding of how this thing works, I always think it's nice to look at a particular implementation of this stuff. And the one I'm going to use here is the Reactive Streams API from the Java language. I think it's now in the language itself as of version 9, I believe. And yeah, so we're going to look at this thing. And this API is made up of these 4 interfaces, and together with a specification of how they interact with one another. And this specification is called the Technology Compatibility Kit, or TCK. And we'll look at how we'll look at some examples of how that works in a second. And already I want you to kind of see this thing is already fairly small and intuitive, right? It's made up of a whole 4 interfaces. It's a lot, and these and you can already guess what these things are doing. So a publisher is obviously something that's pushing data. A subscriber is something that's interested in that data. A subscription represents the one-to-one life cycle between a publisher and a subscriber. And a processor is maybe a little bit more mysterious, but it represents a processing stage between two processing stage, basically. Right, so let's look at the first 2 simple ones and how they interact with each other. So the subscriber calls onto the publisher a method to say, I'm interested in subscribing to you. So a subscribe method. And crucially passing an instance of itself so that the publisher can then use that to call back to it later. And then the publisher then in turn uses that instance to call an onSubscribe method in the subscriber and creating a new instance of a subscription back to the subscriber. And this subscription instance acts as the mechanism by which the subscriber can control the flow of data from the publisher. So subscription has a couple of methods on it. One is request with an integer parameter that specifies how many data items the subscriber wants to request from the publisher, and also cancel for saying, I'm no longer interested in any more results from you, thank you. And yeah, this mechanism by which the subscriber controls the flow through the subscription to the publisher, from the publisher, is known as back pressure, or as another way to call it is back pressure. And that's kind of like a volume control. This is the thing that allows you to turn up the rate of processing or slow it down And it's now just to the dam, the gate in the dam that we saw earlier. And then the final one, processor, is actually something that implements both the subscriber and the publisher interfaces, and it represents the stage of processing in chain. And crucially here, the subscriber is also, the processor is also obviously gets a subscription interface from the stage above, and the back pressure element is preserved through the chain. So the chain of the flow of data through the whole chain is driven through that final stage, that subscriber at the end. And this is very useful because the whole chain is kind of divided by the final bit that needs to actually use the data. And then we can also chain many of these processes together, so to build up our complex functionality of our application. Yeah, and crucially, each stage respects its back pressure element for flow control through the whole chain. And with that, I'm going to now finally, so before we move on to actually looking at some code, I wanted to mention that so Neo4j is reactive to the core. And what I mean by this is that you could imagine, so our drivers are reactive, and you could imagine a situation where we could simulate reactive behavior on the client side, on the driver side, by moving all the buffering of those records to the server instead. But this is not what Neo4j 4.0 does. By reactive to core, I mean that when the request from the client comes in through to the server internals, the internal engine of the server, doesn't generate those results until the client is ready to receive them. So there's no buffering, additional buffering. There's no simulated reactiveness from the client's point of view. There's no buffering on the server, and then this means that the server also has these memory management benefits. And this is important because you don't want to be pushing this problem further up the chain, and at some point you have to deal with those memory if you're simulating this behavior. Yeah. So finally, how can you get your hands on this stuff? So what do we do at on the drivers team at Neo4j? We've implemented Reactive in 3 languages. First one is Java driver, and you've got a choice here between using the Reactive Streams API, the one I've just mentioned earlier, and this other one called Reactive Extensions, which is also another popular one. There's not a great deal of difference between the two. There's slightly different naming conventions, but if you can understand one of them, then you can relatively straightforward to get an understanding of the other, because this ideas are simple, kind of linked together. So yeah, we've got Java Reactive Extensions and Reactive Streams, and we've got JavaScript again with Reactive Extensions, native to JavaScript, and again the .NET driver with Reactive Extensions. And yeah, so let's look at some code finally. So we've got our JavaScript driver, which is and if you're not familiar with the drivers API, it's a fairly small API. The center point being this driver object or a class. And from that class, you can build sessions. We've got 3 types of sessions. We've got simple sessions for that simple imperative style of coding. We've got async sessions for async coding. And then now with 4.0, we've got these reactive sessions. So you create a session, and a session is a container which allows you to run transactions, and you get some certain guarantees about what data is visible within the sessions and those transactions. Yeah, so we create a session. We do session read transaction. The read transaction part allows the driver to do some routing if you're running it in a clustered context, and that allows us to spread the load of the client of the driver to the different nodes that are more eager to handle those queries. And in this read transaction method, we pass in a transaction function, and we run this cipher statement. So we're looking at nodes with a product label and the ID an ID which is matching 0, and we're returning the title from that node. And this records, this next method on the chain, this records method is the one that returns an observable, and observable is essentially reactive extension speak for publisher. It returns an observable that exposes each record returned by the executing query. And then this pipe construct is a nice thing that allows you to chain some more processing together. So here on the map, we're extracting that title out from the results. This materialize function is sanitizing the data into a generic kind, a tuple of an error, and complete it. And then toArray is, as you expect, something that builds all the results, all the titles into an array. And if you're familiar with the previous versions of the drivers, and simple and async sessions, you'll see the rough behavior rough way of usage is very similar as to how it has been for those ones. And yeah, let's look at .NET. So .NET, this is a method that is turning an observable. As I mentioned, observable is essentially reactive extension speak for publisher, and it's very much the same as this first example of JavaScript, right? So we've got a driver object. We do create our reactive session on it, and then we do a read transaction passing in a function, and again running that query, the same query as before. We're collecting our records, and that gives us that observable, all the records returned from the query, and then this time we're also selecting out the title element, or the first item in the record type. And also we've got here some error handling if there's an error in running this transaction, which is just saying that we want to close the session if we see an error. And then finally moving on to the Java example. So here we've got this thing called Flux, which is a Reactive Core, which is from Reactive Core, which is an implementation of the Reactive Streams API we saw earlier. And yeah, again, if you see Flux, think publisher. Essentially, it implements the publisher interface. So yeah, read publisher there. And again, we're doing very much the same sort of stuff. So we've got our query and parameters substitute into the query. And Flux Rectifier has this nice using when construction that allows you to run stuff against a supplier. So, but this is very much still the same sort of logic as in the previous two examples. So we're essentially building a new session. Mono.from supply allows us to create a new session for this chain. We do this again, a read transaction to help us route traffic to the node that we're interested in, and we pass in again a transaction function, and we run the transaction, and then we build up our results again, results.records. And do on next, it adds in a chain, which is this time printing out the string that comes from our result. And then finally, after we finish with this thing, we close the session. It's worth mentioning here, there's if you're in the Java ecosystem and it's particularly using Spring or Spring user, particularly Spring data, we've got a team in our drivers in Neo4j that are working on the Neo4j Spring data equivalent. So if you like your annotations driven and less boilerplate setup for using these things, there's two guys in our working on it, Michael and Garrett, working on some fantastic stuff. And particularly important to mention here because it also is using this reactive framework, so the reactive elements of the Java driver. So that's something really interesting if you're in that ecosystem to check out. And yeah, so for wrapping up, there's lots of examples. There's only a few examples I've managed to show you here. There's lots of examples in the code itself. So if you pull down the repository in the language you're using and look in the examples folder, you'll see lots of examples which you can use to get started. And yeah, it's really the best way to start getting familiar with how this works. But I want to mention here is that you don't strictly necessarily need to use these reactive sessions in order to gain some of these benefits of memory management on client. So simple and async sessions also implement this flow control method. So in flow control mechanism. So there's this buffer on the client which is maintaining in size essentially. So so if you're a previous user of previous version of driver and you want to jump in without jumping into this reactive programming element, you still get benefits from this flow control element, which is really helpful. And finally, for that, thanks very much for listening. And before moving on to questions, I promised you guys some links. So here they are. And this one I think is really the kind of best one. So I was originally trying to wrap my head around this thing. It's a nice gentle introduction for getting your head around reactive programming. Next one is the Reactive Streams specification, which is that those 4 classes and that TCK that we looked at earlier. Reactive extensions link is for the alternative to that. Reactive manifesto, which is the thing that drives the original foundations of this stuff. And then also good resources are this driver's manual, which is full of example code and how to configure drivers to get the most out of them. If you're somebody migrating from 1.7 to 4.0, we've got this fantastic migration guide that will let you know about all the pitfalls and all the issues. And finally, there's the link for the SDN-RX, the Spring Data Neo4j reactive library that you can use. Okay, that's the end of that. Let's see what questions we have. Okay. Okay, I don't see any questions. I see an answered question. And has anybody got any additional questions? There's a question on the chat about async Python drivers, and when that will be available. I think this answer here is, yeah, there's a plan to implement async support with Python. I think that's coming shortly, as well as the 4.0 features for that one. Okay, so if there's no further questions, then yeah, thank you very much for listening, and enjoy the next session on graph data science. Thank you.